So in this video, we will look at prefix-free codes and present this very interesting inequality called Kraft's inequality. Before I begin, let me start by describing what are prefix-free codes. So from here on in this unit, we will look at codes with probability of error 0. So remember we were looking at this quantity L epsilon P bar, the minimum average length of a code, variable length code with probability of error less than equal to epsilon. Now we will look at L bar 0p, where epsilon is set to 0. And since this is set to 0, we basically will abbreviate it as just L bar p. Okay, that's the kind of that's the setting we'll work in. To motivate what is a prefix-free code, I'll present an example. So consider the following code, where your alphabet X has four symbols A, B, C, D, and now you associate binary sequences with this X. So suppose you have 0 with A, 0, 1 with B, uh, say 1 with C, and and let's say 1, 0 with D. Okay, so this is a reasonable code because you have a unique symbol with each associate. You have a unique sequence associated with each symbol in the alphabet. So if you see this output, you'll be able to go back to the symbol of the alphabet. But from practical point of view, this code has a problem. Suppose I tell you that you're not encoding one symbol, but you're encoding a sequence of symbols. So if we encode a sequence of symbols, X, let's say a sequence of length n. So this sequence here is x1, x2, xn. So suppose you encode this sequence using this code, then this code can have a problem. So let's take an example. Suppose, yeah, so what do I mean by encoding a sequence of symbol? Let me first clarify that. So there's an encoder mapping E, which takes a symbol and gives this output as this binary sequence here. And we go over the sequence of symbols and use the encoder mapping E applied symbol by symbol to get the output. So, for example, if the symbols are B, D, that's your X sequence, then the encoded output applied symbol by obtained from this code would be 0, 1 and 1, 0. Now, what is interesting is if you look at a specific example where X is uh, say AC, the encoder output for this particular code would be 0, 1. If I told you that the length of the sequence X was 2, then you will be able to figure out that the two symbols must be A and C. However, if I didn't tell you that length, then you will be confused if the 0, 1 corresponds to A comma C, or does this correspond to B, okay, A comma C or B. Okay. However, as I said, if you tell me the length, then I'll be able to decode. So such codes which can be decoded when you tell the length are called uniquely decodable codes. Okay, uniquely decodable codes. And this uniquely decodable codes are also of practical interest. In many applications, you will store this length n. However, we are often interested in a sort of a faster code, a code where you can instantaneously decode a symbol as soon as you see it. And such property is satisfied by what is called a prefix-free code. A prefix-free code. So I'll now, with this motivation, I'll define what a prefix-free code is. So a prefix-free code is a set C. Okay, this set C for us corresponds to corresponding to the set of code words such that no two so this C will be set of code words. So these are binary sequences such that no two elements, let's say C comma C prime in C, are prefix of one another. So what is a prefix? A binary sequence C is a prefix of a binary sequence C prime if C prime starts with C. So just I'll be perhaps explain this just by an example. So this sequence 0, 1, 1 is a prefix of the sequence 0, 1, 1, 0, 1 because this 0, 1, 1 comes before here and this sequence starts with this. So C is a prefix of C prime. If you look at the first as many bits of C prime as the length of C, they coincide with C. Okay, that's what the prefix is. So a prefix-free code is the one in which no two code words are prefix of one another. So this particular example that we have here, you can see that 0 is a prefix of this code word 0, 1. And in fact, 1 is a prefix of this code word 1, 0. Therefore, this... I apologize for the background noise. These lectures are still being recorded from my home. And so my daughter is there and it's very hard to ask her to remain quiet for a very long duration. Okay. Right. So we now know what prefix-free codes are. Prefix-free codes are those where no code word is a prefix of another, and these codes are of practical interest. You can convince yourself that if you encode a sequence of symbol using prefix-free codes, then you will be able to decode them in that sequence. You will not need to know the length of the encoded sequence, and you'll be able to decode them. So we will be interested in this prefix-free codes, and we will look at this quantity L, let's use this, L bar P, I'm using P, small p for prefix here, prefix free here, of X is the minimum expected length of a prefix free code. So minimum summation over X, Px, the length of the sequence corresponding to X, where E is the encoder of a prefix free code. Okay, so since we are looking at codes with zero error, I can describe it either using this encoder mapping E, because we will have no two code words corresponding to the same symbol because we want zero error, probability of error 0, and or we can alternatively just represent the code by this the code set here, this set of all code words. This EX are called code words, remember, and the set of all EX is called code. Okay. So this C is a prefix-free code, and if you look at the minimum average length over all prefix-free code, that's this quantity LPX. I can also abbreviate this guy here as expected value of E of X, the length of E of X. Okay, so the minimum average length over all prefix-free code E. Okay, so now what we want to understand is how far is this quantity, this one here, L bar P, in comparison with L bar X, when you have no constraints, all you want is zero error. So by the way, these codes where you just have zero error are called non-singular codes. So there are these different classes of codes. If you look at a Cover Thomas book, it will spend some time in distinguishing these different classes. But it's an interesting mathematical distinction. But I think it may not be so important from both theory and practice point of view. So there are uniquely decodable codes, there are non-singular codes, and there are these prefix-free codes. So we'll just look at prefix-free codes. Okay, but maybe for completeness, I can show you how these classes are related to each other. So prefix-free codes are the most restrictive codes, and they are contained in this bigger class of uniquely decodable codes. You can check that if I tell you you can actually decode prefix-free codes even without knowing the length of the input sequence. Therefore, you can decode them if I gave you additionally the length. Okay, and then outside both this is the class of all uh, non-singular codes where no two symbols are mapped to the same code word. Okay, so in principle, this L bar X can be much smaller than L bar PX. Also, uniquely decodable codes minimum average length can be smaller than this. So, just to summarize some result which I'll not prove, it will turn out that prefix free codes are as good as uniquely decodable codes. Whatever you can attain from these codes can be attained from prefix free codes in terms of performance. Um, but there can be code words here which are not here, and we just saw an example, right, of a code here which is not here. And then the non-singular codes, the class is much bigger, so this L bar X can be smaller in principle, but we'll see that this cannot be too much small. Okay. Okay, so just one second. Yeah. Okay, so now we know what prefix free code is and what this metric is. The main theorem we'll show in this part is called the Krafts inequality. Okay. And the statement of this theorem is I'll write. So we consider a code. So we are given a, maybe I'll write a slightly informal version. In the notes I'll share, I'll give a more formal version. So a code C with code word lengths L LX. So this LX is the code length of the code word associated with the symbol X. For all symbols X is prefix free only if, which means if it's a prefix free code, it must satisfy the following condition. Only if, so for any prefix free code, if you sum these guys, this must be less than equal to 1. So what I mean, so yeah, this is a way of writing only if, but what I mean is any prefix free code will satisfy this bound. So if you look at the length of the code words, 2 to the power minus length must be less than equal to 1. Very interestingly, the converse is also true. So what is the converse? Conversely, if you give me any lengths here, these lengths are by the way integers, right? Non-negative integers. In fact, these are positive integers. I'm not allowing empty symbol as a sequence because empty symbol is not allowed in prefix free codes. It will be a prefix to every code word. Yeah, this is just some pedantic argument. So uh, think of a given sequence of numbers Lx. So conversely, given um, numbers Lx, so these are these are positive integers, we can find a prefix free code with lengths Lx with code words of length Lx if if this so that condition is exactly the same as this one. If summation over x 2 to the power minus Lx is less than equal to 1. So the point is that if your lengths satisfy this condition, then you can find a prefix free code with these lengths. On the other hand, if you have prefix-free codes with these lengths, then it must satisfy this condition. So for a prefix-free code, a code is a prefix-free code. This is an informal way of saying it. If and only if this holds. So if this holds, then you can find. Yeah, this is not correct actually. So if this holds, then you can find a prefix-free code which satisfies this. Okay, that's how this theorem is. Okay, this is a very interesting theorem. It basically characterizes the lengths, the vectors of lengths of all prefix-free codes. It says that a vector, this vector of lengths will correspond to a prefix-free code if and only if this Kraft inequality is this Kraft inequality holds. So this thing here is called Kraft inequality. Okay, before I prove it, let me note an interesting implication of this inequality. Zoom out a bit. Okay. So here is an implication. Let me just make it a bit formal. So I'll call it a corollary. Corollary is the lower bound for L bar Px must be greater than equal to h of x. Okay, that's a corollary of this result. So that's very interesting. So even the length of a prefix-free code of an optimal prefix-free code cannot be smaller than h of x. That's a corollary of this Krafts inequality. In fact, if you remember, so we had a lower bound for L bar epsilon p, right? So if you have epsilon equal to 0, then that lower bound is roughly h of x minus log h of x. That's the lower bound we had there. And so what this bound says is that indeed if you go to non-singular codes from prefix-free code, you can perhaps gain something, but that gain can be at most just logarithmic in the entropy. Because because you have a similar bound for this prefix-free codes also. This is not a formal statement. To make this statement formal, we should be able to find a scheme which gets you here. It's only a lower bound currently, which we'll do later. But I just wanted to point this connection here. Remember the lower bound we saw for L bar x. But these are both lower bounds, so we can't conclude anything by comparing two lower bounds. But we'll see a scheme which gets you here. That's roughly the punchline. Almost gets you here. Yeah, that's the punchline. But before that, let's see this corollary. How do you show this from Krafts inequality? The proof is interesting. Before I show Krafts inequality, let me show this corollary. So how do we show this? So suppose you are given a prefix-free code, C. So C be a consider a prefix-free code C with code word lengths Lx. So Lx is the length of symbol x. So we know from Krafts inequality that this inequality must hold, right? So then, what will we do? Look at the average length of this code. The average length of this code, I'll just abbreviate it by L average C, is equal to summation over x px L of x. Okay, that's the average length of this code. Now I'll do something interesting. I will write it as log of 1 by 2 to the power minus Lx. This is equality. This is the important observation here. 1 by this, right? And now I multiply by divide by px. So px log px plus summation over x px log px by 2 to the power minus Lx. So this term looks very much like a divergence, but it's not a divergence because this thing is not a distribution. So I'll make it a distribution. How do I make it a distribution? I just normalize it by, I'll just divide and multiply with this guy. Summation over x 2 to the power minus. This is just to normalize this to make it a distribution, but I have to multiply also here. Summation over x prime 2 to the power minus L x prime. So now this guy is a distribution. So I can express this whole thing as some divergence. But what is this guy here? This is the entropy of x. So I have minus entropy of x. Oh, sorry, make a mistake. I should have 1 by px. Right? Divide and multiply with px. Yeah. So this is an entropy of x. Maybe I should write bigger. Plus, what is this guy? This is some divergence between a p and a q, where q is this particular distribution. This is my q of x. And plus now one more term will come, log of this constant, 1 by summation over x prime 2 to the power minus Lx prime. So this is true for any code word. Now, what is very interesting is that this guy is less than equal to 0 because it's the divergence. And this guy here is, sorry, this guy is greater than equal to 0. And this guy here is also greater than equal to 0. Why? By Kraft's inequality, since it's a prefix free code. So this guy is less than 1, so 1 by this is greater than 1, so this is greater than equal to 0. And that's the bound we were looking for. So what we get is that it's greater than equal to h of x. So the proof just uses Kraft's inequality. It's interesting to also think about the condition for equality. This equality will hold if both these terms are exactly 0, because these are non-negative terms. So if p equals to q, okay, and this guy is exactly equal to 1. So we must have this thing summing to 1 if you have a code with average length hx. If you have a prefix free code with average length hx. So the Kraft's inequality must have equality for such a code. Further, all these probabilities here, px, must equal q. So the lengths must be equal to log of 1 by px. Okay. Equality holds only if Lx equal to log 1 by px for all x. Okay. Now, one thing here is that this log 1 by px is some number, but it need not be integer, and Lx must be an integer. So one thing this result tells us, this simple observation for condition for equality tells us here, is that if you are looking for a prefix free code with average length equal to hx, which is the best you can do, again, entropy, by the way, again, yeah, so I've even stopped remarking about this. Entropy has emerged as a benchmark once again for a slightly different formulation. Okay, so once again, the minimum length you can compress a sequence to using prefix free code, compress a random variable to using prefix free code is entropy. And this equality can only hold if probabilities are such that log 1 by px are all integers. So maybe probabilities are power of 2 or something like that. So there are two ways to view it. One is that, well, we need to be really lucky and this px must be some powers of 2 or something like that. Integer powers of 2, 2 to the power minus 3, 2 to the power minus 5, these kind of probabilities. Another view is that, well, you learn those probabilities, right? It's your model, you know, and perhaps you should learn probabilities which are powers of 2, and that will help to attain this equality here. Okay, that's just a remark. It's a minor remark I have here. Such distributions have a name. I think they are called dyadic distributions. Something dyadic when base is to the log. Yeah, so maybe a dyadic distribution in general, where all log 1 by px are integers. Okay, that's just some terminology. Okay, so we were able to show this lower bound, and this lower bound used Kraft's inequality. So now we will prove Kraft's inequality. The interesting thing about this proof is also the second part, which has hidden in it a scheme, because it says that you can find a prefix free code. So which means I'll be able to describe a prefix free code to you with this given lengths when this is less than equal to 1. So what I will do is I'll give you two different proofs of this theorem, this Kraft's inequality, which correspond to two different schemes. Okay, that's what we will do in the remaining of the lecture, in the remainder of the lecture. Okay, so that's what we'll do. Okay, let me make some more space. Maybe I'll zoom out a bit more. Yeah. Okay, so let's do this proof of Kraft's inequality. Okay. So as I said, we'll use two different construction. The first proof will use a construction which will represent code words using a tree, which is a graph. So I'll describe what a tree is or what a graph is. Okay, that's what I'll do. So graph is a rich mathematical object and it has been studied quite thoroughly, but we don't need all the, we need very basic notions from graph theory for our purpose. A graph consists of vertices or nodes. So these points are vertices or nodes, and between some of these vertices, there are edges. So between some of the pairs of vertices, there are edges. So this, for example, this will be a graph. So in this graph, there are 4 vertices and 1, 2, 3, 4, 1, 2, 3, 4, 5 edges. Okay. In general, you can think of a graph as this pair v comma e, where v is the set of vertices and e is the set of edges. And this E is a subset of V cross V because it's pairs of vertices. So that's what a graph is. For a vertex, let's say this vertex V in this graph, the degree of the vertex V is the number of edges incident on that vertex. So this, it's 3 for this vertex. It's again 3 for this guy, 2 for this guy, and 2 for this guy. We are also interested in the idea of, so we just define what a degree of a vertex is. So degree of a vertex. And we're interested in structures like this, which are called cycles. So cycle basically is a graph where each vertex has degree 2. So it roughly looks like this. So you start somewhere and you end up there. Okay, so that's what a cycle is. So a graph can have cycle, like this one has 2 cycles. This is one cycle and there's another one here, right? So this graph has 2 different cycles. Okay, so this is a graph. What we are interested in is a specific graph which is called a tree. It's not a very clear color, maybe. Yeah, a tree. In fact, we are interested in a binary tree. So I'll just describe that. Okay, a rooted binary tree. So a binary tree has a special node, okay, which is the root node. Start from there, and then this root node has 2 children. Okay, in general, tree is a graph with no cycles and connected. So any 2 points you can connect any 2 points. That's what a tree is. But a binary tree is a special tree where so you start from a root node and then each guy has 2 children. So root, then it's 2 children, the left child and the right child, and then again this is the parent of this node, and then this guy has 2 children, and then 2 here, and then at some point you stop. So you stopped here. So these things are called leaf nodes or leaves. So you have a root and you have all these leaf nodes, 1, 2, 3, 4 leaf nodes. So this is a binary tree. Okay. A complete binary tree. Before I do that, So in a binary tree, you can see that there is this, you can associate with each node a level or a depth. So this is depth 0, depth 1, depth 2, and depth 3. And in general, you can talk of a binary tree of depth D. Okay. So a complete binary tree is the one where there are no nodes missing at any depth. So here you can see these nodes. Potentially you could have added these edges and these nodes here, and then these edges and these nodes here, and then these edges and these nodes here. But they're not a part of this tree. It's as if you have removed these guys from this full tree. So this full tree where you have all the nodes at each depth, that's called a complete binary tree. Complete binary tree of some depth of, let's say, depth D. So question, how many nodes are there at depth D in a complete binary tree? So at depth 1, 2, depth 2, 4, and depth 3, 8. So that's 2 to the power D. There are 2 to the power D nodes at depth D for a complete binary tree. Okay. So what's the connection between a binary tree? Sorry about this. So what's the connection between a binary tree and the code that we were designing? What's the connection between the two? And this is a very interesting observation. We'll take a binary tree and we'll label it. So we'll start from the root, and we'll label the edge connecting the root to the left child by 0 and the right child by 1. And we'll do the same for all the nodes. Left child by 0, right by 1. Okay, this is 0. Then again left child by 0, right by 1. And 1 leaf node, 2 leaf node, 3 leaf node, 4 leaf node. So this binary tree has 4 leaf nodes. Now what you can see is that each of these leaf nodes can be associated with a code word. So look at this path here from root to this leaf node. This corresponds to a code word 1 because you just have 1 here. Look at this this path here. This leaf node corresponds to a code 0, 1. Look at this path here. This corresponds to 0, 0, 1. And then finally maybe you look at this guy here. So that's 0, 0, 0. So it corresponds to all these code words. That's interesting, but nothing so special currently. But what is very important to notice is that actually this code words and this code is prefix free. It has to be prefix free, the way a tree is constructed. So trees actually can be used to represent prefix free codes, and that's why we were studying this binary trees. Okay, so that's just some background that we needed. So from now on we will try to map our prefix free codes to a binary tree. Okay, now back to the proof of Kraft's inequality. So what do we want to show? So we are given a prefix free code of let's say we are given a code with code word lengths, let's say L1, L2, blah blah blah, LM. So M code words for M symbols. So given this, we consider a binary tree, consider a complete binary tree of depth L max. What is L max? L max, I'm just defining it as the max of these lengths. In fact, I'll assume that L1 is less than equal to L2 is less than equal to L3 and LM. So they're already arranged in increasing order. So L max is equal to lm. Okay, that's what I'll assume. So we consider a binary tree of this depth. Okay, so when we do that, sorry, one second. Okay, now it's fine. So when we do that, so when we consider this binary tree of the depth n, so we can draw this binary tree here and see what we get. Okay, so this is some binary tree, complete binary tree, blah blah blah, and then you have this depth which is lm. Now take any code word. Let's say take code word L1. So this is length L1. So let's say we take this guy. So what we will do is we will remove the tree that lies below it. It's also a tree. Okay. We will remove this guy. Question is, when we remove this guy, so we'll remove all these nodes. How many leaf nodes should we remove? How many leaf nodes will we remove? So we'll remove this guy. Okay. So how many leaf nodes should we remove? Well, what's the depth of this tree? The depth of this tree is Lm minus L1. So removed 2 to the power Lm minus L1 nodes. Okay, so this L1 actually, yeah, I'm not saying it correctly. So what is this node here? So think of the code. So this tree we label, this is the binary tree. We label it by zeros and ones as we discussed earlier. Yeah, sorry about this. So we label it by 0 and 1. 0, 1, 0, 1, 0, 1. There will be one code word here. Look at this. This is all binary sequences of length lm. So there will be one code word here of length lm, which corresponds to the code word corresponding to this length L1 code word. So I'm looking at that node and removing all the nodes below it. Okay. Since that node is at length L1, the number of leaf nodes below it will be 2 to the power Lm minus L1. In fact, I've removed this entire tree, but I've removed these many leaf nodes. Right? I've removed these many leaves. The question is, have I removed any other code word? And the answer is no, because all the nodes below it actually have this first code word as its prefix. And none of the code words, so code words will be somewhere here, there'll be one code word here, there'll be another code word somewhere else. But none of the code word will be a prefix of one another. So there'll be no code word here. So this is the code word. Okay. Code word. But no code word here, because otherwise the code word that's here will become prefix of this code word. So we haven't removed any code word. So we keep on doing this for every code word, and we keep on removing these leaves, and we'll have removed no code words. But how many leaves do we end up removing at the end? So overall we remove I equal to 1 to m 2 to the power lm minus li leaves. But whatever number of leaves you remove, you cannot, you have at most these many leaves, and therefore this inequality must hold. And if you cancel 2 to the power lm from both sides, this implies Kraft's inequality. Okay, so this just comes by viewing this prefix free codes on a tree. Okay, where code words corresponds to leaves of a tree. So this is the proof that given a prefix free code, Kraft's inequality, the length must satisfy Kraft's inequality. Sorry, this is less than equal to 1. Now the converse argument is exactly the reverse of this argument. I will not write it. I've written it in my notes. I'll share the notes. I'll just describe it here. So the converse argument is exactly a symmetric argument. You're given these lengths, and these lengths satisfy Kraft's inequality. I'll make this complete binary tree of length lm, and now I'll choose this code word one by one. So first, what I do is I'll choose the first code word of length lm. This is the leftmost code word. I can just do that, and nothing is removed. Now I can still find another code word of length lm minus 1. I'll choose that and remove everything below it. And then I can still find code word of length uh, lm minus 2. I can choose that and remove everything below it. I can keep on doing. The only thing I need to show in this proof is that why am I still able to choose this one more code word? And that's where this Kraft inequality will help to show that you can choose one more code word, because if you cannot choose, then you must have exhausted all the leaves, and and there's some little account keeping you can do, and which would have implied that Kraft inequality doesn't hold. So yeah, I'm just saying this very fast, but essentially the proof rev- just reverses this argument. Okay, so the bottom line is, if you have L1 to Lm satisfying Kraft's inequality, then you can find these code words which are represented on this binary tree, uh, and therefore they are prefix free. That constitutes a prefix free code. Conversely, given a prefix free code, you can represent it on a binary tree, and you will get the proof of Kraft's inequality. Okay, this is one proof of Kraft's inequality. Now I'll present another proof of Kraft's inequality, which uses a different representation. So this one was representing code words with tree, but we can have another proof which uses a different representation. That's also interesting. So this is proof 2. And it uses interval representation. Okay, the proof is essentially the same, will turn out to be essentially the same at the end, but it will represent the code words it will represent the code words in a very different way. It will represent them using using intervals. So let me describe this proof. So we are given these lengths, let's say L1 to Lm. We are given, maybe I'll do it in a particular way. Okay. So given again code words, okay, sorry, not code words. Given a code with code words of length L1 to Lm. Okay, given a prefix free code, consider, now what we consider is an interval associated with each length. Consider the interval so I'll associate one interval with each code, with each length, and as before I'm assuming here L1 is less than L2 is less than Lm. Okay, actually maybe I'll write it differently. Yeah, so for each code word I'll consider this interval IC. This is the interval corresponding to the code word C. This starts, so this is an interval in 0, 1. It's a subset of 0, 1. It starts with 0.C1 CL, where L is the length of the C. It starts there, and it ends at 0.C1 C2 CL plus 2 to the power minus L, where this guy here is the binary representation of a real number. So you can think of it as a binary real number. So just to quickly concretely describe this number in binary represents half, just like we do decimals, half plus 0 into 1 by 4. Cleanly. So half into 1 plus 0 into 1 by 4 plus 1 into 1 by 8. That's what this binary number represents. Similarly, you have this binary number 0.C1C2Cl, which we are taking a code word and associating with it with this binary number between 0 and 1. And this is another binary number, but plus 2 to the power minus L. Okay, that's the interval we have. Note that all the binary sequences which have this C1 to Cl as its prefix. Okay, they start with this C1 to, they must start with the C1 to Cl and have something after that. All these sequences lie in this interval. That's the important observation. Okay, IC contains all the binary sequences, all the numbers, all the real numbers. Let's say 0. Some other C1, C2, and it can have any length, Cl prime. Okay, such that this number, this sequence, has C as its prefix. Okay, so all the prefixes are here. And what's the length of this interval? It's 2 to the power minus L. So for each code word we can have these intervals, and all those intervals must be disjoint, because this is exactly the set of all sequences which have C1 to Cl as its prefix. And since the code words are prefix free, the interval corresponding to two different code words are disjoint. Alright, and all these intervals are contained in 0, 1. So there are disjoint intervals in 0, 1. And therefore, if you add their lengths, which is just 2 to the power minus L, lengths of these intervals, then that must be less than or equal to 1. And therefore, 2 to the power summation over I 2 to the power minus Li must be less than or equal to 1. Okay? It's a rough proof. So this is one observation. This is my first observation that I have here for the proof. Second observation is that so this is actually so this first observation implies so the intervals I see corresponding to different code words for a prefix free code IC intersection IC prime, or maybe IC prime is fine, is empty for two code words C, C prime which are not equal to each other, because they are not prefix of each other. If there's anything, if they actually intersect, then you can show that there is a code word. So what happens if they intersect? If there is a point in their intersection, that means there is a point, there is a binary number like this which has C as its prefix and also C prime as its prefix. Okay, and this can only happen if either C is a prefix of C prime or C prime is a prefix of C, which is not true, and therefore this cannot happen. Okay, and then this is the main observation, and the second observation after this is simple. So the length of interval IC is 2 to the power minus L, where L is the length of this code C. Okay, and so therefore you have disjoint intervals of length to the power minus Li within 0, 1, and so their sum must be less than or equal to 1. That's the proof. And once again, this proof can be reversed. You can construct a code prefix free code if you're given the lengths by using exactly this. So what you do is you first start with the first interval, which is 0 to so let's say the first length, let's say L1. So you will start with 0, 0, 0, let's say, plus 0, 0, 0 plus 2 to the power minus L. How many zeros will you take? exactly as as much as many as L1. So you have the next point, and now you take the the next point on the right, okay, and this plus 2 to the power minus L. By the way, what is that? So if you have 0 0 0 L zeros and 0 0 0 plus 2 to the power minus L, what is this number here? That's exactly the number which has 1 at the 2 to the power minus uh, Lth, at the Lth position. Okay, maybe I can do the converse. This construction is actually important. We will use it later for arithmetic code. So conversely, given L1 LM such that their sum is less than equal to 1, we can construct a prefix free code a prefix free code as follows. So what do we do? So first code word is take L1 zeros. So 0 0 0 L1. So yeah, so this can be a first code L1 zeros, and now we associate with this first code word the interval I1. I'm just calling it I1, which starts with this 0 0 0. Of course, that's what is 0.000. So it just starts with 0, right? It starts with 0 and ends at 0 plus 2 to the power minus L1. Okay. So what is this number here? This is 0.000, and it has 1 at the L1th location. Okay. Now, what is I2? I2 will start at this point, this particular point. So this thing. So this is C1, and then C2. C2 is a code word of length L2, by the way. So I'll start here 0.0001, and I'll add zeros to it. By the way, again, the assumption is L1 less than L2 is less than Ln. So yeah, so I can add more zeros to make it of length L2. This is C2. So it has 1 here and then more zeros, and then this is of length L1, L2, and this 1 is at L1th location. And once again, to this number, I have the same number again, 0.001 plus now 2 to the power minus L2. So now the next one that you have is at the L2th location. And now we continue this procedure. This can be my next code word, C3. This is 0.000 and then again 0.001, and this 1 is at L1 location, L2 location. Okay, and you keep on doing this, and you can notice that none of these code words is a prefix of each other. Okay, and why can you keep on doing this? Why can you have LM code words? Well, the length of each interval is 2 to the power minus L2, and so there's always some interval left here, so you can define the next interval. Okay, and because of Kraft's inequality holding, there's always an interval held here, and you can define the next one and keep on going. So that's how you can find this code word corresponding to these lengths if they satisfy Kraft's inequality. Okay, so I went through this in a sort of an informal way, but the scheme I hope is clear. In my notes, I'll give more details, but I think it's better to understand the scheme by examples and in this manner. And of course, the proof is it's simple, but when you write it formally, it looks just lengthy. Okay, so to conclude, let's go back to the statement of the theorem. So what we have shown in this lecture is that prefix-free codes satisfy Kraft's inequality. The lengths of prefix-free codes satisfy Kraft's inequality. And conversely, if you give me lengths that satisfy Kraft's inequality, then I can find prefix-free code with those lengths. And because of this result, what we now, so we have a scheme of constructing prefix-free codes. If you give me lengths that satisfy Kraft's inequality, so all we have to now do is just to look for lengths that satisfy Kraft's inequality, and we'll be able to find the prefix-free code which satisfies. We will be able to find a prefix-free code. Okay, and the benchmark that we have is this entropy of x. The smallest prefix-free code possible must have must still have average length greater than entropy of x. Okay, in the next class we will see a scheme which will give a prefix-free code with average length very close to entropy of x. So see you in the next lecture.